So for the remainder of this morning's session, as you can see in the program, we're going to have our third and final keynote talk in the first theme, followed by our first panel discussion addressing that theme, and that will take us up to lunch. So, if I could introduce the third keynote speaker, Tim Lenton is the Director of Global Systems Initiative and the Chair of Climate Change and Earth Systems Science, University of Exeter. And he's lost a voice a bit, so he's mic'd himself. Thank you, Tim. Oh, speaking, of course, about tipping points in climate and biosphere function.
Thank you, Janet. Thanks for all the organizers for having me. Give me a speaking slot. So I'm going to give you a tour through tipping points in climate and biosphere function, an issue which we tend to problematize. And I guess as we're in the threats and challenges session, and I've spent 10 years sort of training myself to be an ever more effective horseman of the apocalypse, I might do a bit of that. But like the previous two speakers, I actually want to flip the narrative around and talk about how we can tip transformative change, or at least I hope we spend the rest of the 2 days focus more on that. But let's remember that we're only here, having a conversation, breathing an oxygen-rich atmosphere because there have been some changes, some fundamental changes in Earth history caused by the biosphere, the co-evolution of life and the planet. And in the case of oxygen in the atmosphere, it didn't rise smoothly. We now understand it as having gone through at least 2 major tipping points in Earth history. One of them is called the Great Oxidation halfway through the planet's history. The other one we're still trying to understand and is tangled up with the rise of animals 600 million years ago and snowball Earth events that we might also consider an extreme kind of climate tipping point. But as we look ahead, we certainly problematize the situation now. We're tending to see negative tipping points. We're tending to suspect that we're somewhere over here in a little boat, perhaps without a paddle or with a meager paddle, floating down streams, thinking there's probably some dangerous tipping points ahead, and we've no idea how close they are. And we need to change course before we get to here, because there's a lot of inertia and lock-in in the system. So ideally, we'd like some early warning signals of what's coming before we get to the critical dash line. So one of the ways I've tried to think positively about tipping points is, even if they're bad tipping points, we can get early warning of what's coming. And to illustrate that, I just do a little mathematical cartoon model where we start with a system with 2 basins of attraction, 2 alternative states, subjected to some stochastic noise, and eventually it's going to tip from one state to the other. And before it does that, actually it's showing some warning signals that a tipping point is coming, and it was slowing down in response to those fluctuations it was getting from its environment all the time. And I hope you could kind of see that visually. And we were measuring that on the bottom as this rising indicator of autocorrelation in time in the system. And mostly I'm going to talk about how we might use that to forewarn us of bad things that are happening. If we were imagining we might want to tip positive transformative change in ecosystems back to a preferred state, we might be able to use the same indicators to know when and how to effectively intervene to tip positive change. So next, a little tour through scales. Just to tell you what you might already know, but that we're living in a world of complex systems nested within complex systems and nonlinear dynamics. And so sometimes, not all the time, but sometimes, systems are sensitive, and they're so sensitive that they can exhibit this tipping dynamic. And that can happen for coupled biological, physical systems across all sorts of scales. So down at the population level, that's kind of well known. And indeed, some experiments done right back in the 80s and repeated more recently show that classic cases of tipping a collapse of a population, like this case of photoinhibition, it's called, of algae shading other algae in a chemostat, show warning signals before the collapse. In other words, the system recovers ever more slowly from the same perturbation the closer you get to the tipping point. If we step up scale a little bit, ecologists in the room are well aware that there's at least more than half a century of work on alternative regimes or stable states and associated tipping points for ecosystems, particularly aquatic ecosystems. That picture there of experimental manipulation of a lake on one side of the divider and not on the other, showing two alternative states, eutrophicated and oligotrophic lake states. That dates back to the 70s. More recently, Steve Carpenter, other colleagues have been showing that in experimentally manipulated lake systems where we know that there's the possibility of tipping points, that indeed with experimental manipulation you can convince yourself that early warning signals before the tipping point, either to a eutrophic state or for what's called a trophic cascade in the food web. And there's some work on finding these signals in historical cases of before historically observed abrupt shifts of lake ecosystems or of land systems that change state. Carrying on up, and perhaps adding debate as we go, but there's a lively discussion about whether we could tip large-scale biome change. There's certainly evidence for multiple modes of tree cover for a given rainfall level right across the tropics, and that's what these plots are getting at. So for a whole range of rainfalls around the tropics of the planet, you can find high tree cover states, known otherwise as rainforests, and low tree cover states, known otherwise as savannas. Now, how much of that bimodality in the data reflects a true bistability, which means a true underlying self-amplifying feedback that can separate these two attractor states? Well, that's the thing that's under debate, particularly as us humans are collectively entwined in the system and disturbing it by changing things like the fire regime, where fire is one of these key feedbacks that is reinforced, if you like, by the grassland state and suppressed by the forest state. Well, suffice to say that some of the nice recent work, like this paper by Bert White, is showing that indeed, if you factor humans in the equation, some of the bimodality is to do with the correlation of human interference with the state, but there's still some true bistability, certainly in the Amazon region. It may be less spatially extensive, and there's still an open question over what the true mechanisms of feedback here are that separate the attractors, as we would say. Of course, my pet thing has been an even larger scale, where something like the prospect of alternative states and tipping points of the Amazon is just one of several candidate tipping elements in the climate system, defined as being kind of at least subcontinental in scale, some of them quite physical, to do with the purely physical nonlinear dynamics of say, the Atlantic's meridional overturning circulation or the feedbacks involved in losing an ice sheet. But others being very, very biological, including the Amazon and the coupling of Sahel vegetation to the atmospheric circulation and the monsoon regime. And we came at this map from like 3 different sources: evidence that these subsystems had shown abrupt shifts in the past, and/or evidence from models that we saw abrupt changes in the future in complex models, or thirdly, that our fundamental understanding of the processes involved would give us reason to believe that the self-amplifying feedbacks in some of these systems were so strong that they could give this tipping behavior. Well, 10 years on, and lots of work has been done trying to work out how close are these candidate climate tipping points. Actually, this work was 10 years ago. It was an expert elicitation where the experts were given 3 different temperature corridors into the future. That's less than 2 degrees, that's 2 to 4 degrees centigrade, sorry. Oh, I'm British. And that's 4 to 8 degrees high-end warming. And these black bars are individual experts' imprecise probability estimates of the likelihood of tipping 5 different tipping elements. Maybe we should just say concentrate on the Amazon rainforest dieback for this talk. And predictably, as the temperature goes up, the experts' assessment of the likelihood of tipping goes up. I think the key take-home message from that was, whilst economists on the climate problem had assumed that tipping points were high impact but very low probability events, this expert elicitation, even if you take the most conservative assumptions, says that if we carry on business as usual, the lower bound probability on the likelihood of one of these 5 tipping points is already 56%. It's more likely than not. So it's high impact, high probability event. And in mid-warming, it's the lower bound probability is around 16% with the most conservative assumptions, so it's still a relatively high probability event. More recently, some colleagues have been digging around in the climate models from the last IPCC report and finding lots of abrupt shifts at sort of regional scale, shall we say, within the models. And the striking result from that was that a load of those abrupt shifts are clustered somewhere between 1.5 and 2 degrees of warming above pre-industrial, which I don't think any of us has quite understood where that's coming from. I've got my suspicions of why that's the case. And that's to do with how we've tuned our models in the past to be stable at the present climate, but we didn't push them too far. There's a bias here because we have less scenarios going up to high warming, so you have to imagine reweighting the distribution, which brings this up as a second peak, but still this is a distinct clustering of abrupt shifts at low-end warming. So, yeah, it's a complex coupled system, right? So you tip one bit of it, it probably has some causal repercussions for other bits, and that's what this map is about, again from the expert elicitation. And what was slightly worrying was there were slightly more mathematically positive causal interactions between tipping events than mathematically negative ones, because if we change that language to the emotional language, the mathematically positive is the emotionally negative here. It's the possibility that tipping one thing increases the probability of tipping another and another, and the dominoes falling in a cascade. I'll say a bit more about that, because the world can't be so unstable that that's the norm, because we wouldn't be here to talk about it if it was. But yeah, there'll be more on that. It means that when friends and colleagues put out a picture like this, I have a lot of caveats about it as a co-author. The idea that there might be some sort of global scale tipping point. I wouldn't say that this is accurately described as a tipping point to a hothouse Earth, but I would say as climate scientists, there's a potential tipping point to a wethouse Earth, where at modest levels of warming, we know we could commit the irreversible loss of major ice sheets and tens of meters of sea level rise that will be very difficult to reverse. It'll take a long time to unfold, but I think there is some truth in that. And in a true risk analysis, we can't rule out possibilities of global scale tipping points, given that we've seen them in Earth history. And indeed, when you look at the recent ice core record of Antarctic temperature and CO2 over the last 650,000 years, if you took the labels off the scales and gave the plots to an electrical engineer or maybe a cardiologist and you asked them how stable the system was, if they know their subject, especially the electrical engineer, they'll tell you this is not a super stable climate system because it's oscillating between these two bounds and it's doing this sawtooth oscillation. It flicks out of the depths of the last ice age incredibly abruptly, and it would appear that the self-amplifying feedbacks rule the day temporarily before the system is again bounded in the interglacial state. So my take on it is the climate system is actually unusually unstable. At the time that we come along and we push it up to here so far and up to there in my lifetime, and who can deny that, even to a non-scientist audience, who would deny that that was going to have some serious consequences? Anyway, let's get back to early warning signals then. So let me go back into the Ice Age to show you that there have been lots of abrupt climate changes during the last Ice Age, 20 odd of them called Dansgaard-Oeschger events, including at the end of the Ice Age. If we zoom in at the end of the Ice Age, there's one here, it's called the Bolling warming or the Bolling-Allerod warming, the cool Younger Dryas interval, then an abrupt warming into the Holocene, the current interglacial. And just cherry picking now, but we've gone back and looked at these past abrupt changes, and we've looked before them to see if there were early warning signals of what was coming. And here I'm going from about the depths of the last Ice Age through to the end of the Younger Dryas, but I've cut out the final transition out of the Ice Age, the final abrupt shift. There's a few issues, for sure, detrending the data, but there's a very strong early warning signal of slowing down in the climate dynamics before the end of the last Ice Age. And even if you took out the problems here, detrending the data, it's very clear that there are longer-lived fluctuations in the climate here than there are back here, and that's a signal that something big was about to happen. We've also gone into model worlds to convince ourselves that in our models we can force something bad to happen. We can force, in this case, a collapse of the Atlantic overturning circulation. Part of the surface manifestation of that is the so-called Gulf Stream. So we force this model, we add fresh water to the North Atlantic until we break the overturning circulation up there takes a while to switch off. Then we look at the pattern in the fluctuations before the collapse, and we see that the system slows down and the fluctuations slow down before the collapse happens. And we can get a reliable warning indicator of that, and we can get a reliable warning indicator at exactly the latitude where we've spent millions of dollars and pounds putting in a monitoring of the overturning. Turns out not to be the best place to look for the signal, but it works there. Now, ecologists, obviously if there's a climate tipping point, there's going to be bad consequences for ecosystems. And this is just, could have shown you many things, but this is, if we force that collapse of the overturning circulation, what happens to the productivity of grasses in our rather crude model of vegetation within the Hadley Centre model? And basically, it's a big hit on net primary productivity in the growing seasons across Europe. What I want to turn to now, though, is, well, what if you don't believe me? Maybe the climate tipping points really are, still low probability events. Could we all agree, though, that we might learn something interesting about how climate variability is changing by applying these same kind of methods of time series analysis? And might that have some importance for ecosystem change? So what I've done here with Chris Bolton is we were just looking at the observational data of sea surface temperature fluctuations. And be very careful here, there's a lot of infilling of the data in the southern hemisphere, but it's better where the ships have been on regular ship tracks in the northern hemisphere. Basically, we're seeing a pattern where there's a lot of slowing down of sea surface temperature fluctuations where it's actually monitored for a long time across the North Pacific and the North Atlantic, which surprised us. So we looked in a bit more detail, especially at the North Pacific, because the pattern of sea surface temperatures in the North Pacific and how it oscillates around that pattern is a well-known thing called the Pacific Decadal Oscillation Index. That's what it looks like. And who knew that if you just run the analysis on the NOAA Pacific Decadal Oscillation Index for the last century or so, you find out that there's a very robustly rising autocorrelation of that data set, which is another way of saying a slowing down of the fluctuations in the sea surface temperature. There's also rising variance, which then drops off again more recently. Why should I care, you might be thinking. But, so what's that? That's saying that the whole sea surface temperature variability is becoming slower. Fluctuations are more prolonged. They're also overall increasing in amplitude. Well, that's got to matter for the ecosystem. And the default position in most models of the simple models of the marine ecosystem is that it has a time scale probably governed by the zooplankton of around 2 years. And your typical ocean fluctuations probably had a 6-month time scale at the start of this in the early 20th century. But the ocean fluctuations have been slowing down over time. So their time scale's coming towards that of the ecosystem, which means we see in a simple model, we see the ecosystem become more correlated with the climate variability, which means its variability tends to go up. Even if there's no increase in variance in the forcing, the variance in the response will go up because the ecosystem is integrating this slower forcing. And I'd like to sort of put it out there that maybe that has something to do with why we have had very well-known abrupt shifts in North Pacific ecosystems, and that the most famous ones were in the later 20th century. Those became more likely, I would submit, because the sea surface temperature variability had slowed down. We've done some more analysis of the observational record. The kind of orangey red areas are showing this increasing variability in observational climate. This is the models projecting into the future. What happens to temperature variability intermonthly in the high-end warming scenario? Look at these hot spots that come out. 40-odd% increase in temperature variability over the Amazon at the end of the century, and about a 20% increase in southern Africa. Big decrease where the Arctic sea ice has gone, so it's no longer making its contributing role to temperature variability. I'll just focus in on the Amazon as my final example. Well, of course, we know climate variability is doing crazy things over the Amazon. There have been striking droughts in the last decade or so. We have some models saying that the Amazon has alternative states, not all models, but not just this model. Carlos's model also has alternative states. In the Hadley Centre model, you can warm the climate, and you don't see any response in the forest, but you've already made a committed change in that model world to a large loss of forest, when you're at 2 or 3 degrees warming and you've barely seen any dieback, because the forest is lagging the forcing, it's lagging the climate. We asked whether there were early warning signals of that in the model world, and there aren't the conventional ones because the timescale separation isn't there. The forest is being forced very quickly relative to its natural timescale as trees, but we can find a system-specific early warning, which is that basically a given temperature perturbation causes a larger loss of carbon if it's a warming or uptake of carbon if it's a cooling when the baseline temperature goes up. And we could use that as a warning signal that things were getting worse for the Amazon. 48 seconds to go to return to the topic then of putting this into an economic analysis. The point I was trying to make in response to Chris's talk, because we've done some work where we've tried to put stochastically uncertain tipping points in the loss of ecosystems into the famous DICE model that Bill Nordhaus just got a Nobel Prize for. And the long and the short of it here is a model like that has a welfare or utility function. It can include unsubstitutable qualities of the biosphere and ecosystems and non-market values. And when you do that, even with very small, relatively low risks of a relatively small loss of non-market benefits that are unsubstitutable, it can radically increase the incentive to mitigate climate change, expressed as what level to set the carbon tax at in the model. So let me wrap up, 7 seconds to go. If business as usual continues, then climate and biosphere tipping points are expected to become high-impact, high-probability events. Early warning systems exist. They don't always work, but they can be used as an aid to adaptation. This isn't just about climate change, it's about our life support system, the ultimate source of all our flourishing, and I think that change in the narrative is essential, and we should shift to talking about how we could tip transformative change in the right direction for social and ecological systems. Thank you. I sinned on the red. Chris.
I wanted to come back to your comment where you were skeptical about the Stefan et al. Idea that we might drift into a hothouse world, but then the idea of the tipping points, it clearly pushes us in that direction. And I guess the one way to think about the issue is, does there need to be a truly catastrophic outcome in order to provide a strong warning signal? But then I guess another question to be curious about your thoughts on is, are there other mechanisms that you've thought about but didn't tell us about that decrease the risk of really dropping off that cliff?
I think yes to the final question without elaborating on it, because the earlier question is a key one, which is really, are we facing an existential threat or not? I think we are, for what it's worth, from all the work I've done across system science, the history of the planet, not just what we're doing now. I'm not sure that existential threat is rightly framed, as I say, not just about climate change. I think it's absolutely about reframing, as the other speakers in the discussion has hinted, it's about reframing this as this is our life support system that we're fundamentally perturbing. And it's got along well without us, and parts of it, the microbial parts, will carry along fine without us in the future. But I really think we are, I don't know how to put it, but I honestly think from my own work that we are running a serious risk to our current mode of well-being. Yeah, fundamentally. And although I took the narrow path there of framing, of going through that climate framing to is it a hot house or is it a wet house, I think it's much better that we're here together as ecologists as well as climate people, because the real existential threat is if we lose the information and the memory and the creativity that's carried in the biosphere. Yeah, Chris.
Chris Thomas from University of York. If I'm speaking here as a kind of amateur reader or some of the paleo.
Yeah.
More than places.
Yeah.
3+ billion years ago.
I can hear him. It's all right. I'll repeat the question. Oh, yeah, sorry.
Oh, right. Okay. Sorry. Okay. If you go back to 3+ million years ago, before the Pleistocene, the climate does not appear to be spectacularly unstable, and there was lots of ecosystems and diversity. I wonder if you could comment about the future in the context of the deeper past 3 to 10, 15 million years ago.
Yeah, absolutely. Because for those that don't know it, I'm a student of Lovelock and of Gaia and of Earth history, and so I spent a lot of my career trying to work out, does the Earth have mechanisms by which it's come to self-regulate on long timescales? And I believe it does, and I've written about that again recently. And when I look at the pattern of Earth history, it fits our current models, that it's a pattern of long periods of relative stability interspersed with short intervals of tumultuous change. And so the bottom line question is, am I right in suspecting that I have some evidence that the Pleistocene and the Quaternary is a signal that actually the Earth system's heading into one of its unusually unstable phases and is more vulnerable to perturbation than it normally would be? I tried to make a little bit of that case in the talk. I've written a whole book on it called Revolutions That Made the Earth, if you want to bore yourself going through that. But yeah, your point's well taken, because warmth is not de facto a bad thing if you have time to adjust to it. And many of my colleagues have used the Paleocene-Eocene thermal maximum as 55 million years ago as a reason to wring our hands in horror at the consequences of 1,000 billion tons carbon emission. But any paleobiologist who's good will tell you that the Paleocene-Eocene thermal maximum was a time of the origin of 3 major mammal orders, including our own, the primates. So from our biased perspective, it wasn't a disaster, it was a formative event. And I suppose in broad part terms, that's what I'm wrestling here with you, is, tipping points are not value laden as a given. They can go one way or the other, and beauty's in the eye of the beholder, or those who are the beneficiaries of the changes that unfold. This little thing is about, hold on a minute, we're becoming aware of all that. I think we have the option to put a level of self-aware self-regulation into the system. That's what we're debating here, and in many such meetings. Yeah, right at the back, sorry.
I think my question follows on that. I was very interested in that map you put up that showed a variety of different tipping points in different systems around the world. There was one in this, I think it was the Sahara. There was a greening of the Sahara.
Possible, yeah, which would have been the one that might be framed as positive.
And so, yeah, so my question was, so I think it's very appropriate that we would tend to focus on the downside, because that's where the risk is, and that's where we should be more concerned. Having said that, it seems to me it begs the question, to what extent do you think it is possible that if there's less research into the sort of positive, tipping points, to what extent do you think that those are out there? And in terms of biodiversity, I don't think there would be one, but in terms of carbon storage, there's a lot, there are things going both directions. So I'm curious if you can comment on that.
Oh yeah, thank you, because that's exactly where I'm trying to get to with this. That, as I said, I think communally we've got very good at telling the apocalyptic narrative ever more apocalyptically, and I think we have somewhat biased our what we've chosen to focus on. And I think if I was to summarize the discussions that were already started at this meeting, is that many of us are all struggling to or trying to find a constructive narrative. And what I'm submitting here is that tipping points can be part of the vehicle of a constructive narrative. Some tipping points that might unfold in a changing climate might not be entirely bad. The specific case of the Sahel, greening or not, is fiendishly difficult because our global climate models generally rubbish at capturing even the past observed climate variability, especially in the Western Sahel. And when you take, say, the few models that are any good for the present and project them forwards, they diverge. Some give a wetting, and others give a collapse of the West African monsoon. So we honestly don't know which way that's going to go. Suffice to say, in the last few decades, the trend is obviously shrub growth and wetting and greening at the moment. But no, the broader point is the crucial one you get to, which is if we agree, maybe out of the meeting, maybe not, that we want to work towards changing the narrative, then we need to be actively finding and articulating those stories of tipping change in the right direction, if that means, and that of course might imply deliberate intervention in an already degraded coral reef ecosystem, for example, where, as we were discussing before, we know we've got some control over some local factors, even if we can't easily change the dial on the global temperature. So yeah, that's where I think we want to go, and I think if we had taken a more unbiased look at our predicament, we probably would find more stories where not everything is a disaster in what we project as it is. Yo, Nancy. 1 minute 40 seconds.
Hi, Nancy Knowlton, Smithsonian. So this might not be a fair question, but I was wondering if these methods have been used to analyze social discourse, social media, news coverage, to inform our understanding of social tipping points.
I have with colleagues, Hal Williams especially, done some work on that, actually with a data company, with a partner who actually had other, let's say, larger companies asking exactly that question to them, sent on to us, which may be why I haven't published that, at least yet. But I can tell you that there are, in the Twitter sphere, there are early warning signals of what in network language we would call collective attention being focused on an issue like climate change. So what you see is typically, even on an issue like climate change, if you map it as sort of users and hashtags, even people talking about climate change have segmented into a modular network of the people who talk about the land stuff, the people who talk about the ocean stuff or whatever. But prior to a big surge of collective attention on social media, you see the network structure changing and the modularity being lost. And that subgroup, who you've already identified, focus, come together to talk about an issue. Then boom, it goes ballistic. This is, to caveat that, this is because they know that the release of the IPCC report or something is coming. So it's not sort of a total early warning in the sense that it's without foresight of something coming. But it is quite interesting to know, if you want to think in network terms about solutions, that we can monitor, that we can basically monitor networks, social networks, and we can map our thinking of network metrics into this tipping point dynamical systems form as well. And I think we can use that, again, potentially to say, when is the sensitive point at which to intervene with a new idea or a new innovation, when the system's going to be most sensitive to tip it into something better. Thank you. The light's back on.